Hello students, welcome back. So now we are going to be studying binomial distribution. This distribution, it falls in the class of discrete probability distribution function. And what it does, it describes the number of successes in a fixed number. This is the key word, in a fixed number of independent experiments. Another name for experiment is trials. In this case, this is important to remember that it will be a fixed number of experiments, and also it's going to be independent. One experiment will be completely independent of the other experiment. Here, each trial has only two possible outcomes. Now, these outcomes, they are usually called success and failure. This is the terminology that is used in binomial distribution. Now, let's understand this through a simple example. Suppose you toss a coin 4 times, and here I define my success as getting ahead. So here, my each toss is independent experiment. This one right here. So if I toss one coin, let's say I toss this coin, then I toss another coin, then what I get in this coin has no effect. It does not depend on what I got in the previous toss. That's what you mean by independent experiment. Here, I'm conducting four independent experiments because I'm tossing the coin 4 times. So in this case, my fixed number of experiments is 4. Now, in this particular instance, I can get zero success. In other words, I can get zero head. I get tail, 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 and tail. All fours are tail. Or I can get one success. For example, I can get tail, I can get head, and then I can get tail, tail. So this could be one outcome. Or I can get two success. For example, I can get head, tail, head, tail. So I think you got an idea now. So these are the different possibilities that I can get. Now let's take a look at another example. Suppose you pick 4 random emails from your inbox, and here you define my success as getting a spam. So here picking each email is independent experiment. So in this particular instance, I'll be conducting 4 trials. I'm picking 4 random emails. So in this case, I can get zero success, meaning there is no spam, or I can get one success, meaning there is one spam, or two success, two spam, three success, three spam. So for example, I may get like the first experiment, I get a spam, 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 and non-spam. By the way, I can also go. It can also go like this. This could be, let's say, spam, and this could be spam, but this one could be non-spam, non-spam, and then this would be spam. So I can get like that too. So spam, spam, non-spam, and spam. So these are different ways you can actually get this. Then I can also have 4 successes. In other words, all 4 emails are spam. Another example would be this. Suppose you pick 4 random items from an assembly line for inspection. You're doing quality control. And here you define success as getting a defective piece. So here picking your item, that would be an independent experiment. Here I'm doing 4 experiments right here. So I can get zero success, meaning there is absolutely no defect, everything is good. Or I can get one success, or I can get two success, or three success. Three success will mean three defect, 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 or non-defect. Or I can also get non-defect right here. Okay, I can get defect, defect, and defect. So I can have these different combinations right here. So 3 defects can be this one, or it can be this one. Now, there are a few key points about binomial distribution that you should be mindful of. Number one is that it is a fixed number of trials. So the number of experiments that you do, it is predetermined. It's already known to you. For example, in our previous case, that was right here, I'm actually defined my number of experiment as 4. Next one, you can only have 2 outcomes. Your outcome can be the success or failure. There is no third option. Constant probability. What it means is that your probability of success is always going to remain for every single trial. So if your probability of success generally is denoted by P, and the probability of failure is generally denoted by Q. Q in this case would be 1 minus P. Independent trial. It means that the outcome of one trial would not affect the another one. For example, when you're performing coin tosses, well, what you get in the first one, it would not affect what will happen in the second one. Also, in this case right here, when you're picking up these defective pieces, the probability of you picking a defective piece in the first one has no effect. It will not influence the probability of picking a defect in the second piece. So each one of these trials are independent of each other. That's what you mean by independent trials. Now, in binomial distribution, you're going to hear the word random variable, and generally random variable is denoted by x, and that would be your number of successes in your n trials. So in this case, you will see something like this written sometime in the textbooks, x, and then you're going to see this fancy symbol, binomial n comma p. Your n would indicate the number of trials, and p would indicate the probability of your success. Now, the number of ways of choosing k successes from n trial is given by this expression right here. So, for example, there are 6 ways of getting 2 head in a 4 coin toss. So, in this case, my n would be 4 and my k in this case is 2. So, when you solve this, this will come out to be your 4 factorial divided by 2 factorial times 4 minus 2 is 2 factorial, and you solve this, this is going to be 1 times 2 times 3 times 4. This is going to be 1 times 2 times 1 times 2. And when you solve this thing, the answer will come out to be 6. So there are 6 ways of getting 2 head in 4 coin tosses. These are your possibilities right here: head head tail tail, head tail tail head tail tail head, and this one and this one. You can see that they are total 6. Now here, my PMF, which is also called probability mass function, is given by this expression. So the probability of getting x equal to k, in other words, probability of getting k number of successes, would be given by this expression. This one right here is same as this right here. Now suppose you toss a coin 5 times and the probability of getting a head is, let's say, 50%, is 0.5. Question: what is the probability of getting exactly 3 head? Well, in this case, my n equal to 5, my probability p equal to 0.5, and my k, that defines your number of successes, is 3. So substituting this in your formula, that would be this right here. The answer will come out to be 0.3125. So it's 31.25% chance that you are going to get 3 head, if actually exactly 3 head, if you toss this coin 5 times. 1, 2, 3, 4, 5 times. Let's take a look at another example. Suppose there's an assembly line, it produces machine parts. Now the probability that a part is defective is, let's say, 20%. Now, 3 parts are selected at randomly and they are independent of one another. So, what is the probability that exactly 2 parts are defective? Here we have 3 experiments. So, here your n equal to 3. Now, the success is getting a defective part. So, in this case, I want to know my k. So, my k in this case is 2, because that's what I want to try to find out. What is the probability of getting exactly 2 parts that is your defective? So, substitute your values: n equal to 3, k equal to 2, and your p equal to 0.2 in this expression, and your answer will come out to be 0.096. In other words, you have 9.6% chance, 9.6% chance that exactly 2 parts are defective. Now I will show you how you can calculate all these, like PMF, probability mass functions, and all those things using Python. So the first thing I do is import my NumPy, also import my visualization library, and from my SciPy, I'm importing Binom. This is an inbuilt method that allows you to perform, or that allows you to calculate your binomial distribution. So suppose the question is given to you is this, that you toss a coin 5 times and the probability of success, in other words, getting head, is, let's say, given to you as 50% chance. So the question is, what is the PMF? What is the probability mass function? Also, you want to know what is the probability of getting 3 head. So in this case, I specify my n. In this case, my n equal to 5 because I'm conducting 5 experiments. So define your x in this case. This will be number of successes. So my successes can be 0, 1, 2, 3, 4, or 5. Also define your p. Your p in this case is going to be the probability of getting a success. In this case is 50%. So all you have to do is just call binom, and from here call the inbuilt method PMF and give your x, give your n, give your p. This is going to compute your probabilities. And when you print out your probabilities, these are the numbers you're going to get, these ones right here. So what do these numbers they mean? Well, the first one, that would be this right here. It means the probability of getting 0 head. That would be 0.03125. The second one is the probability of getting 1 head. This one is the probability of getting 2 head. This is the probability of getting 3 head, 4 head, and 5 head. That's what this means. And now I want to plot them. I want to see how exactly they look like. So in this case, I'm calling bar plot. Supply your x and supply your probabilities, and also giving color equal to yellow. Put some labels, x and y labels, and plot your graph. This is how your graph looks like. So in the first instance, 0, that is the probability of getting a 0, if you recall, was 0.03125. So this number right here is that number right here. The probability of getting 1, that would be this one right here, is this one right here. And the answer was, if you come over here, was 0.15625. Likewise, the probability of getting 2, that would be this right here, would be this number right here. Coming back, you can see that is 3125. So this would be 3125 right here. And likewise, probability of getting 3, 4, and 5. You can also do the same thing using stem plot. So in stem plot, all you have to do is just call plt.stem, supply your x, supply your probability, and this will give you exactly the same result. So sometimes some people prefer bar plot, some people prefer stem plot. So they also give you basically same gives you different little visual representation of the same data. So in this case, probability of getting 0, probability of getting 1 is this right here, probability of getting 2 is this number, and these are your probabilities over here. Now, this binomial distribution, it is widely used in your machine learning classification, also for quality control testing, for A/B testing, and also for medical trials.